Hi, this video is for understanding strong and weak acids. Why are some acids, strong and, can cause harm to us if we were to get them in our eyes, whereas other acids we're able to, drink. Lactic acid is in our milk and citric acid's in our sodas. Um, has everything to do with what we call acid strength. If an acid is strong, then it will break up like 100%. And you can see that in this picture. Like hydrochloric acid is not going to stay HCl. It's really going to break into H positive ions and chloride ions. So 100% are going to dissociate. So some strong acids that are common are hydrochloric acid, nitric acid, and sulfuric acid. So a strong base is kind of similar. We aren't talking about hydrogen ions though, we're talking about hydroxide ions, but if it is a strong base, then it will break up into, dissociate completely. So if you look at, again, this drawing or, model, the sodium hydroxide, they're all broken up into the sodium ions, which are the purple, and the hydroxides, which are the, the pink and white. So examples of strong bases are sodium hydroxide and lithium hydroxide. So any group 1 metal, hydroxide, and group 2, calcium, strontium, and barium those hydroxides are all strong bases. So weak acids like carbonic acid and acetic acid that we have in foods and drinks and things, they are an acid, so they have to produce hydrogen ions in solution in water, but they don't dissociate much. So this picture, and I know the resolution isn't the best, but this is showing you that most of the carbonic acid stays together as the full compound, which is the green, and then they do break into, one of the hydrogens will come off, and then you'll have the rest of the hydrogen carbonate anion. So it has to break apart to some extent, but most of it doesn't if you have a weak acid. Similarly with weak bases, they will stay together and not dissociate, similar to a weak acid. So the generic way that we write the dissociation for a strong acid is we would write our equilibrium, it's a reversible reaction, but it lies to the right so far that we don't really draw the little back arrow. If we did, it would be teeny. So it will break into hydrogen and then whatever the anion is. So that could be, H could be nitric acid, breaks up into hydrogen ions and nitrate ions. And if we were showing this in water, and I'm going to use the HA example up here, you would want to just show all of those separated. We wouldn't draw any intact HA. So they're all broken into ions. Sometimes we look at the relative number of moles. So if you start with a strong acid, over time, when it dissociates, this goes away. And then you have the hydronium ion, which is interchangeable with the hydrogen ion and the other anion. So we say that equilibrium lies to the right, which just means that the products are favored. And we also say, like, if we were to tie these together, so if this is the strong acid, which is our Bronsted-Lowry acid, then it's tied to the base, which is our conjugate base. So it's very likely to donate a hydrogen ion but it's very unlikely for the anion, to accept a hydrogen and go back to HA, since the HA really wants to dissociate. So that makes this a weak conjugate base. So A is not likely to accept a proton and go back and form HA. So a weak acid, sometimes we do HW, doesn't matter really what you use, but after some time has passed, you can see that some of it dissociated into the hydronium and the anion, but most of it stays together. And again, if we look at and tie them together the way we do when we're identifying the Bronsted-Lowry acid base, conjugate acid base, this is my Bronsted-Lowry acid, this is my Bronsted-Lowry base, just like the previous one, conjugate base. But this one is not likely to donate a proton. It wants to stay together, whereas A is very likely to accept a proton and go back and form the HA. So we say that the equilibrium lies to the left. So that would mean if I were drawing my double arrows, I would draw a really big back arrow because the forward reaction isn't really happening to much extent. So we are going to have mostly reactant, which would be the intact together acid. So we have something that we call Ka. It is similar to Kq, and what we do is we write the equilibrium expression like we normally would, and if I were going to write the Keq for this, I would write, remember we write the products, remember the brackets are the molarities, so it's the product of the molarities of the products over the reactant, and the water is a liquid, so remember we don't include that in our equilibrium expression. So because of that, we end up with a equilibrium expression like I just wrote. That equilibrium expression, because it's an acid, we give it a special, instead of calling it Kq, we call it Ka, and it's still the same thing. So the only thing to remember is that the water, because it's a liquid, we're not going to include it. So if you have a strong acid, it's going to dissociate and you're going to have a lot of the products. So your Ka value is going to be large. If it's a weak acid, then you're going to mostly have the intact together acid, and being on the denominator is going to give you a very small value of Ka. So we can look at the Ka values in a table that you are going to have a copy of, and you can see they write the generic formula for the Ka. In this case, it's an acid that we call Hb instead of Ha, but same thing. It's a hydrogen ion, at least the first hydrogen ion in the acid, and then the anion B. And again, I'm going to show you. So remember, this would tie over here. And anyways, I guess you don't have to tie it together right now, but if I write the equilibrium expression, I'm going to set this equal to 1, and this is what I would get. And when I get this, if I have a lot of this, because it does dissociate, it's a strong acid, then I'll get a large Ka. And if I don't, then most of it will stay intact, and I'll get a very small Ka. So you can see these are Ka values that have been determined at 25 degrees Celsius. So all of these are very strong acids, they're going to dissociate almost 100%. And then as we go down, these are weak acids, and the value of the Ka, the smaller it is, the weaker the acid. So, in summary, a strong acid is going to dissociate 100%. The equilibrium lies to the right because you're going to break up. The Ka is going to be very large. The conjugate base will be weak because it's not likely to reform the acid. And if we draw it, we would draw it all broken apart. Summary of a weak acid. Now we have the double arrows because it can go both ways. You're going to have all three present. So in my drawing, you're going to have HW, the acid that stays together, and then some of it has to dissociate or it wouldn't be an acid. Equilibrium lies to the left because you're going to have more of the intact together acid, and the conjugate base is strong because it's likely to accept a proton and go back and become the acid.